Anybody here who doesn't speak Polish? No, to mogę chociaż przedstawić naszą prelegentkę po polsku. Dzień dobry Państwu dobry wieczór na ostatnim konwersatorium przed świętami i w tym roku. Mamy dzisiaj super temat i super wykładowcę. Mianowicie panią profesor Joannę Kiryluk z Uniwersytetu w Stony Brook w USA. Oryginalnie od nas. U nas robiła pracę magisterską i pracę doktorską, no a potem losy ją rzuciły za ocean. Te dwie prace były z fizyki spinowej, z doświadczeń spinowych robionych w CERN-ie. Joanna potem kontynuowała tę tematykę w USA czas jakiś, a teraz od kilku lat zajmuje się fizyką neutrin i bardzo specjalnym eksperymentem, który jest zestawiony i pracuje na biegunie południowym, gdzie zresztą była sama i opowie o tym Państwu również. Wykład będzie po angielsku. To już prosimy Joannę.
Dziękuję. Chciałabym podziękować za zaproszenie. Również profesor Barbarze Badełek za wiarę we mnie, gdyby nie ona. Również Ewa Rondio, z którą pracowałam w CERN-ie nad moim doktoratem. Gdyby nie wiara we mnie, prawdopodobnie nie byłoby tego wykładu dzisiaj. Więc raz jeszcze chciałabym podziękować swoim kolegom i Państwu za przyjście tutaj na ten wykład. Rozumiem, że to jest tuż przed świętami. Niestety u nas trwa teraz sesja, więc wcześniej nie było możliwości. Wykład będzie po angielsku, ponieważ ja mam problem z mówieniem po polsku na ten temat. Nie mam po prostu doświadczenia w mówieniu po polsku. Być może powinnam zacząć. Okay, so today I'll talk about a very special experiment which is called IceCube. And it's a detector in a very special location. It's in Antarctica, specifically at the South Pole. And the goal of this experiment is to discover and measure flux of astrophysical neutrinos. So far, before IceCube, the only known source of neutrinos from outside of our solar system was supernova, 1987, and nothing else. But there are theoretical predictions that expected neutrinos to be produced in astrophysical sources, and that's basically the goal of this experiment. So before I move to IceCube itself and the location, I'd like to briefly introduce neutrinos. It will be a very basic level. So what are they and what's the history of neutrinos? So we know that matter, as we know, it's only roughly 5% of known stuff in the universe. Neutrinos as themselves are not part of atoms, but they are produced in radioactive decays. In standard model, which is the model of fundamental interactions, we know that there are three neutrino flavors: electron, muon, and tau. And it is assumed that in standard model, these neutrinos are massless particles. So they were discovered in the beta decay, so negative beta decay in 1914. So what was discovered that if a nuclei parent decays, then a daughter is produced and the electron, and the expected spectrum of the electron was expected to be a constant just from basic energy and momentum conservation, but it was measured to be continuous. So physicists had a choice either to discard the energy conservation, which was very hard to do. So instead, in 1930s, Pauli proposed a new particle of zero mass to explain this continuous spectrum of beta decay. At that time, Fermi developed a comprehensive theory of radioactive decay, and that included a point interaction where a neutron decays into basically these three particles. In modern days, this point-like interaction is no longer valid, so especially in higher energies, this neutron decay goes through the weak interaction, and the boson which carries the weak interaction is W minus or Z, which are the force carriers for electroweak interactions. So neutrinos were discovered in 1956. The experiment it was a famous experiment designed to specifically discover anti-electron neutrinos. So these are coming from reactor. In the reactor, we have products of fusion that are neutron heavy. So we basically have lots of neutrons. When they undergo negative beta decay, then they produce anti-electron neutrinos. So what they proposed was to capture these anti-electron neutrinos. They would interact in water and produce a neutron and a positron. So now we have two products, neutron and positron. Positron will be captured by atomic electrons and will produce two photons. Neutron will be captured by cation, which is a strong neutron absorber, and will produce a single gamma. So the signature to observe this product of decays are two pulses of gammas, which are separated by a few microseconds. So the rate was found consistent with the Fermi theory, and this new E has been confirmed to be a massless or almost massless particle. And this discovery this detection was awarded a Nobel Prize. Now, are they really massless? So here I just want to limit to one slide, which assumes two flavor neutrino oscillations. We know that there are more than two, so there are three and possibly more, which are called sterile neutrinos. But so far, no sterile neutrinos has been detected. So what does it mean? That in the 60s, a theory was developed that neutrinos are created as a flavor eigenstates, but propagate through space as a superposition of mass eigenstates. So the mass eigenstates are numbered 1, 2, and in case of 3 neutrinos, there will be a third one. And the weak states, so electron neutrino and muon neutrino, are just a mixture of these mass states. So of course, in this model, it's assumed that only neutrinos that are massive, that they can oscillate. And just to remind you, in standard model, it's assumed that neutrinos are massless. So now, why this neutrino oscillation model was developed? In the 60s, there was a discovery of a deficit of solar neutrinos. So solar neutrinos are produced mostly in pp chain reaction in the sun, and it produces electron neutrinos. Compared to the expectation of the standard solar model, there was observed a deficit of solar neutrinos, but it was just an indication that the number of electron neutrinos are somewhat low. And it took many years until basically 2001 when SNO first detected clear evidence of solar neutrino oscillations. So another set of experiments which studied neutrino deficit was the atmospheric neutrino deficit, and in this department there is a strong group which participate in Kamiokande, in super Kamiokande. In the 80s, they discovered a deficit of flux of atmospheric neutrinos. They are produced in pion decays, which are produced in the cosmic ray showers interacting in the atmosphere. So the majority of neutrinos are of muon flavor. And again, it was discovered that there is a deficit of flux of these muon neutrinos. in the 1998, Super Kamiokande discovered the evidence of atmospheric neutrino oscillations, and this was just recently awarded a Nobel Prize for the discovery of neutrino oscillations and the evidence that neutrino have masses. So this is definitely physics beyond standard model. So now, for the purpose of this talk, we want to talk about neutrino astronomy and how we want to use neutrinos to study universe. So why and how? So we're interested in, we know that there are particle accelerators, which are cosmic accelerators. The examples are AGNs, or maybe supernova explosions, or more recently, some events which, like neutron star mergers, which produce gravitational waves. They're also expected to produce neutrinos. So basically, you can study the process of acceleration of particles in this cosmic sources using different probes. So cosmic rays, gamma rays, neutrinos, and until recently, so gravitational waves are possible with the LIGO experiment. So here I would like to focus on neutrinos. Basically, neutrinos have the advantage over gamma rays or cosmic rays is that they travel, they're transparent to basically most of the energies of the universe. So what happens with gamma rays, the currently observed gamma rays energy spectrum from, for example, Fermi satellite, the highest energies are TeV photons. Even if higher energy photons are produced, they will interact with cosmic microwave radiation, and that will lower the energy. So for photons, the maximum observed energies is TeV. For neutrinos, we don't have that. We don't have that problem, so we can go much higher with energies. And with cosmic rays, they're charged particles, so they will be bent in magnetic fields. So it's very hard to point them back to sources. So what are the sources of neutrinos? The atmospheric neutrinos. So for if we want to study cosmic ray, cosmic neutrinos, we want to understand the background, and atmospheric neutrinos are background for the search of astrophysical neutrinos. So we need to understand this very well. Solar neutrinos, supernova neutrinos, these are typically very low energy. So for IceCube, my experiment, it's outside of the acceptance, so we go into much higher energies, and these are not the sources that we can study. So what are the alternatives? Galactic sources, extragalactic sources, or so-called GZK neutrinos, so the highest energies neutrinos, which we will interact with when the cosmic rays interact with microwave cosmic background radiation. They produce these very high energy neutrinos, but so far they have not been detected. So what is the prediction for neutrino fluxes? So fluxes tells you how many particles you can expect depending on the energies. So for solar neutrinos and supernova neutrinos, fluxes are relatively high, but they are, as I mentioned, they're typically occurring in low energy. At higher energy, what IceCube is focusing on is this range where we expect an excess of those coming from the astrophysical sources to be above the atmospheric background. So there is a band which is called the Waxman-Bacal band, which tells you basically what is the maximum flux expected from these astrophysical sources. And now if we want to reach this very high energy particles, which is 10 to the 19 eV, if we wanted to do this on Earth, then the LHC accelerator should have a circumference of Mercury in order to reach this kind of energy. So it's a really, really high energy. So it was discovered that we can make neutrino telescope to study these ultra high energy particles, neutrinos, by doing optical detection. And this method was proposed by Markov in the 60s. So they proposed to install detectors deep in the lake or the sea and to determine the direction of charged particles from Cherenkov radiation. So how does it work for neutrinos? I'll explain in a bit. So first, the Cherenkov radiation. Well, it was first observed in the 30s when Cherenkov was asked to look for effects of radioactivity in liquids. We know that the Cherenkov radiation is emitted depending on what kind of medium a charged particle is traveling from. So there is a condition on the threshold velocity when this effect can happen. So a particle will emit light, which forms this Cherenkov cone, and it will depend on the refractive index for the medium. So for water and for ice, which I'll talk about, this angle is rather large, is 41 degrees. Now, what is the underlying physics for emission of this Cherenkov radiation? When a charged particle travels through the medium, it will polarize molecules. And depending on the speed of the particle, these charges can be symmetrically distributed or anti-symmetrically distributed. So in one case, there is no Cherenkov emission. In the other case, there is a Cherenkov emission. And what is the spectrum of light producing this Cherenkov radiation? So you can see that this is the peak is in the blue light, so that's why there is this blue glow for the particles that emit Cherenkov radiation in mediums like water or ice. Okay, so now how does it work for neutrino? How do we want to study neutrino? How do we want to observe neutrinos? Neutrinos don't have mass or very small mass. They don't have charge, so how do we observe them? Well, the neutrino needs to first interact in order to destroy itself and then produce particles in the final state. So in the final state, we can have electron, mu1 or a tau in terms of charge-current interaction. And these particles, so the products will travel through the medium, produce the Cherenkov radiation. And I should mention that the energy emitted as a part of Cherenkov radiation is very tiny. So most of the energy losses occur in the medium, but what we see is only this Cherenkov cone, and this is what we want to detect with optical modules. So in this case, so for electron neutrino, when it interacts in the ice, it produces a mu1 and some hadronic cascade. And this mu1, when it travels through the medium, will lose energy and will emit these photons. So now the medium typically is water or ice. So there are existing detectors that are deployed in water, and there is one in ice. And the location is at the South Pole. So now I want to talk about Antarctica and the South Pole because I promised pictures, and then I will move to IceCube detector and the results from IceCube. So now what is the Antarctica? Well, it's the opposite of Arctic, and it's one of the coldest, windiest, highest, and driest location in the world. So the climate is, well, low temperatures, but I should mention that low temperatures, it's also a relative quantity. So for IceCube, our main location where all the data is sent is in Wisconsin, Madison, Wisconsin, in the US. And I was told that scientists from there actually like to travel to Antarctica, to the South Pole, because winters are actually better there. It's summer at the South Pole. It's very harsh winter in Wisconsin. It's actually much warmer in Antarctica than in Wisconsin. So the area is roughly 45 times the size of Poland. It's a thick continental ice sheet, roughly at the South Pole, it's 3 kilometers thick, and then it hits the rock. The average elevation is 2,000 meters. So when you land actually here, it's like you're landing in the mountains. It's really dry there. It's really cold. There's no humidities, and there are lots of mountains. So I traveled to the South Pole, which was in 2009. Here you can see the average temperatures in. So this is unfortunately, in Fahrenheit. So here you have the scaling. So with the wind chill, it's roughly minus 50 to minus 60 Fahrenheit. All right, and since it's in the south hemisphere, then the summer there is winter here. There is a very short amount of time where people actually can travel to the South Pole. It starts mid-October to mid-February. This is where planes can actually land there. Outside of this period, the planes cannot land. So those people who stay for winter, which lasts like roughly 12 months, there is basically a very short period of time where planes can deliver food, fresh veggies, etc. Otherwise, so outside of this period, they just run out of these luxury items very, very quickly. So how do we get to the South Pole? So first, you need to travel to New Zealand, and then you use the military plane to get to first the coast of Antarctica. For the US, it's called McMurdo Station. So you basically fly in this military plane, which is rather big. Then you land at McMurdo Station. So this is how it looks like. It's basically a set of buildings. It looks rather industry. But the advantage of being here is that you can really enjoy the life, because at the South Pole there is nothing. So when we arrived to McMurdo, well, basically when the ice is frozen, this is the airport, and then you travel by this bus to the actual station, and these are like barracks where you can stay for the night. So this is called luxury accommodation because you are allowed to take showers every day. If you go to the South Pole, that's not the case, and I'll talk about this later. So at McMurdo Station, as I said, you can see the penguins, birds, seals. It's actually a very nice place to walk around. And then if you want to fly, those lucky ones who go to the South Pole, the planes are smaller. This is how it looks inside of the planes, and these are basically pictures of the mountains and how does it look on the way to the pole. So now the South Pole Station, it developed over years. So the South Pole first was discovered or reached by 2 expeditions. There were 2 competing teams. I don't know if you're familiar with the story. one by Amundsen, the other one by Scott, and they were basically racing who will first get to the South Pole. So Amundsen, which was the Norwegian expedition, Scott led the British expedition. So the Norwegian one reached the South Pole in December 1911. For Scott, it took longer time because it was a well-funded expedition, so they were required to collect data on the way, samples on the way to the pole. And the Norwegian one, it was just one goal: go as fast as you can to reach the pole. And the sad story is that when Scott reached the pole with 4 other men on the way back, they unfortunately ran out of resources and they died. So since the South Pole discovery or reaching the South Pole, there were basically some Navy station, which was a very limited facility. Then it was upgraded to the dome, and the dome was there until basically 2008. So the first physics experiments, there were barracks inside this dome. So it was pretty harsh and rough. And then the National Science Foundation decided to build like a really nice station, which, as you can see, it's elevated because at the South Pole, the winds are actually not so strong, but the snow accumulates, so you can elevate the station once the snow accumulates. So this is how it looks like. There is a ceremonial South Pole. So this is where everybody takes pictures, and we're actually checked when we depart the South Pole that everybody has a picture. Like, you're not allowed to leave without a picture at the ceremonial South Pole. But the geographic South Pole actually moves, so every year there is a celebration to move the pole because the ice sheet moves. So it's roughly 8 or 9 meters per year. Now, how does it look at the inside the station? So I was lucky to get a room in the station because most of the people stay in the barracks outside. So in summer, there's the South Pole station can accommodate roughly a limited number of people. The rest are put in barracks. So if you want to use facilities, you need to get dressed, put your gear, boots, and warm parkas, and then you can walk to the bathroom and use cafeteria. So ice cube shifts were happening in one of the rooms. The cafeteria, actually a competition to become a chef in this station is very fierce. So it's the position that people are fighting for, to be a chef and cooking there, which is not an easy task because the food is frozen and you need to prepare the menu 2 weeks in advance, and you need to plan like what will defrost, how fast. I mean, energy is a scarce resource there. So there is a gym, so you can exercise there. There are lots of activities. There's a quiet reading room if you want to read. There is a greenhouse. So this was actually developed with the Mars missions in mind. So the South Pole, the extreme isolated location, is used for also astronauts or people to test the psychological effects of isolation and how people would behave in this very claustrophobic environment. So post office, you buy stamps which are local US. So all the trash which is collected there, everything needs to leave the South Pole station, so nothing can stay there. So trash, if someone by accident brings an insect like a spider, we're supposed to take it back to the coast. So nothing is supposed to stay there. So as I mentioned, the resources are very scarce. If you want to use water, well, the water needs to come from a melted ice. And how can you melt ice? You need to transport fuel. And this fuel used to be transported by planes. I heard that nowadays they use trucks. So trucks go from McMurdo Station to the South Pole. And this is basically to deliver enough fuel so that it will last for the winter. So the consumption of water power is monitored. And basically, so here you can see actual and the goal. So people basically are asked to behave and use less. So everybody's entitled to 2 1-minute showers a week. So that means two minutes of continuously running water. So you can soap yourself and then turn off the water and then you can rinse. So there are no timers. So it's just basically everybody is expected to behave. So people or scientists who are at the South Pole take shifts to help the chef in the kitchen, to wash the dishes, to clean the bathroom, and all the stuff. So we do all of this. Now I mentioned that there is a summer camp. So this is how it looks like. There are these barracks where people can sleep. And that basically in the summer there are approximately 300 people who can stay there. In winter there are 40, 50 people. So it's a significant difference. So for a comparison, in McMurdo Station it's roughly 1,000 or 1,500 that come to stay there. So transportation, well, it's actually fun, but we used to walk alone. So here you can see like there is a warning for a beacon flashing. That means the plane is coming. So during summer there are a few planes that used to transport fuel. And then I was told that one of my colleagues, like long time ago, like created a problem for a plane because he was thinking physics, did not pay attention to the surrounding. And after that, they put a sign like, please have a look, and put a flashing beacon when the plane arrives, because the airport or the runway is basically next to the station. So we also do fun activities like the celebration of a new year. So there's a race around the world. So that means race around the pole. So you can easily do it. Ice cube. Well, this used to be a dormitory which was placed inside this dome, which was used for accommodations before. Now it's reused for the ice cube counting house. So basically, all signals that come from the detector are processed in this counting house. So now I want to talk about the ice cube experiment. The collaboration consists of roughly 300 people, and it's growing. 48 institutions, 12 countries, basically all around the world. So if you have people in Europe, US, Japan, and Australia, and New Zealand, it's the telephone conferences are a challenge, but we somehow manage. So where is the ice cube located? So the station is here, and then this is the skiway where planes land. And then if you want to get to the counting house, you need to either, if you have an equipment to drive, then you can, or you just walk. Yes, and this area indicates where the ice cube is deployed. It's not deployed on the surface, it's deployed deep down. So how deep down? So this is the surface. The ice cube consists of 86 holes. and each hole is instrumented with 60 optical modules. But the instrumentation only happens, so there is a 1,500-meter ice cap and 1 kilometer, which is actually instrumented down. The separation of the string is roughly 120 meters. The separation of the optical modules is roughly 17 meters, and it was optimized for optical properties of the ice. So this 17 meters is roughly consistent with the scattering length of the light in the ice. And 120 meters, that's what was assumed for the absorption length of the ice. So these were based on measurements made with Amanda. Amanda was a smaller detector, which was like a prototype for IceCube. And an interesting thing that happened with Amanda when they first deployed the strings, they didn't go deep enough to 1,400 meters. It was lower. And basically, with this detector, you could see no light. So our PI, Francis Hausen, now is joking that, well, the first experiment which we proposed, what did we observe? Nothing. Everything was black. And we didn't understand why this is happening. So of course they trusted the initial measurement and the theory of how far deep you need to go down in order to ice impurities to disappear. So what happens close to the surface, there are small bubbles that basically scatter light so much that you don't see any light. So then someone decided to do calculation, and the calculation indicated that if you go like 500 meters further down, then all these impurities should disappear. And this worked. So the test was done with one string, and with this one string, it was extremely successful. We could see a neutrino event, but it was, yes, I think it was a very hard beginning of the experiment. Like, what do you do if you see nothing? Like, how do you explain it to your funding agency? So now, how IceCube was constructed? It took several years to construct. Now the requirement was that drilling and deploying should take roughly 2 days. If you want to complete this in a few years. Of course, this was driven by the cost. If you have 1,000-ton equipment that needs to be shipped by plane to Antarctica, it's significant. So even transporting cable, it's a challenge. You cannot do this in one season. It has to be distributed. And then, well, you need basically a system that could heat water to roughly 90 degrees. If you want to melt ice and create a hole that is so deep. So these holes are roughly centimeters wide. The water refreezes, so you don't want this water to refreeze before you finish deploying your detector. So it was optimized for that as well. So here I have a video of how this drilling works. So the first layer is called firm ice. So a special drill is basically snow. So you need to use a special drill to get through the first 50 meters. And then it starts the hot water drilling, where you basically go 3 kilometers down. So again, not everything went smooth. Sometimes there were. So maybe I'll stop here for a second, because it's a funny story. So when they were drilling one of the holes, they hit some frozen meat that was dropped some time ago, because in winter there are airdrops, so they can drop stuff, but the planes cannot land. And apparently one of the packages was like deep there. How this happened? Well, of course, not 3 kilometers down. It's closer to the surface, but that created a change in the design. They had to move the hull because they hit something that could not be moved. All right, so let's continue here. So here you can see what is required. So this is one tower which is being moved to a location. So at the end of the season, they move the equipment to the location of the next hull. Here you can see the heated water that goes through this hose, which is very, very long. And yes, it's basically it's very challenging task. So it took lots of iterations to make this efficient, and at the end of the seasons, we were managed to really speed up the drilling time, because it saves cost, which is important. So here you can see. So this is hot water drill, and then follows the optical module deployment. So they were all tested and prepared. So there is significant testing done in the lab, and then they are retested at the location. So all of them need to operate in like extremely low temperatures. The power is expensive. So 5 watts is how these optical modules operate. So there was a requirement of the power usage, and then you can see how they are being deployed. All right, and of course, well, here you can see how dedicated people are. It's not always easy, even though it's considered to be very quiet at the South Pole compared to the west, to the coast of Antarctica. I don't know if you've seen a movie called The March of the Penguins. If you haven't, it's a really nice picture about penguins, coast of Antarctica, and how strong the winds can be and how harsh conditions can be. So South Pole is much nicer in this respect. All right, so South Pole, it's a really excellent medium for neutrino detection. One of the problems is that we need to measure its properties, because it's not like you can design your material. The material is given. And one of the challenges is that there are dust layers which come basically from the volcanic activities. So you can see all these depths up to 2,200 meters. These are like eruptions of volcanoes that created these ice impurities, and the biggest one was 74,000 years. So now, how does IceCube see neutrinos? There are different signatures. So for muon neutrinos, we only see the product, so the muon track, and it has an excellent pointing resolution. The energy resolution is slightly worse. For electron and tau neutrinos, we observe the so-called electromagnetic and hadronic cascades. So the light is distributed in a spherical way. So this is how it looks like. So there are two completely different signatures. And so these are complementary. We don't have really angular resolution to search for sources with electron and tau neutrinos. We can do this with muon, but this kind of events can produce an excellent energy spectrum. So what kind of backgrounds do we expect? The goal is to measure astrophysical neutrinos. One background, which is also a neutrino, is atmospheric neutrino, but the majority are atmospheric muons. So basically anything that comes through the Earth get rid of atmospheric muons. So if so the direction is one way of distinguishing whether the muon comes from the cosmic ray muons or whether it comes from atmospheric neutrinos. What are the expected rates? It's basically 27 kilohertz. Atmospheric neutrinos, we detect one every 6 minutes. Cosmic neutrinos, which we've discovered recently, is one every month. So it's a very significant ratio of cosmic ray background to the actual signal. This is how it looks 10 milliseconds of data in IceCube, so it looks like complete mess. And you need to look for a needle in the haystack. This is actually an atmospheric muon neutrino event. So what you see here, these dotted lines are strings. These dots are the light signal from individual optical module. The size of the bulb tells you how much charge was deposited, and the red color indicates that it's earlier, and the blue light indicates that the light arrived later. So we've measured very precisely atmospheric neutrino flux. For electron neutrinos, it's still challenging because the rate is not so great. The majority are muon neutrino. And now I want to come to the final part of my talk, which is how did we discover the cosmic neutrino flux. So this happened in 2012-13. And then we first discovered PeV electron neutrinos. So just to compare the LHC, the center of mass for LHC is 13 TeV. These are neutrino events of roughly PeV scale. So these are the highest energy neutrinos that have been detected. And it created some exposure in the news. So how do these PeV energy cosmic ray cosmic neutrinos look like? So they look like a sphere. So we found these one cosmic neutrino event in 2012. Now here I want you to see what is the size compared to the map that you're familiar with. So we're somewhere here. And this is the size of the PeV neutrino event. So it's rather big. So now I want to focus on the diffuse neutrino astronomy, meaning that we want to measure the flux of these neutrinos. And basically the idea for this measurement is that you want an event which starts inside of the detector. So if the vertex is somewhere inside of the detector, you're basically sure that this is a neutrino event. So the first result that we've published is for all neutrino flavors combined. What you see here is the number of events. This is for 3 years of data as a function of energy in TeV. So here you can see these PeV events. So far we've collected 3. Now what these lines show, the blue histogram is the predicted background of atmospheric neutrinos. The red one is still some contamination from cosmic ray muons. And the rest basically is unexplained flux, which in our case, the only flux that is unexpected and we want to measure is the cosmic neutrinos. So this is basically an evidence that we are measuring the flux of cosmic neutrinos. Now, how do we convince ourselves that this is cosmic ray neutrinos? Well, if we look at the angle distribution of all of these events, basically in this part, these are the events that go through the Earth. So in this part, we would expect to see when we when we move to high energies, to neutrinos start interacting in the Earth, and then we will see the Earth absorption effects. And in this case, we will see the atmospheric cell vita. So atmospheric cell vita, neutrino cell vita, what does it mean? That typically, if neutrinos are produced in cosmic ray showers, they're accompanied by cosmic ray muons. So if we get rid of muons, then by definition, we'll also get rid of those atmospheric muon events. And this is why all these predicted background events, so muons and neutrinos, are suppressed compared to those which go from a different direction. So now, as I said, here we look for atmospheric cell vita effect, and here the Earth absorption. So what we will expect, that even for astrophysical neutrinos, if we increase the energy, this should go down, and the same holds for this part. So now the quantity to look at is the deposit energy. So if we focus on hundreds TeV events, we see a significant drop. If we increase this further, so 140, you can see that all these data events start to drop. And basically, if you go sufficiently enough, you can still see these events, which are clearly an indication of cosmic neutrinos. So now the not so good part is that everybody were expecting to see some correlation, or if you plot the position of these events on the map, so this is in the galactic coordinate system, so this is a galactic plane. Then you see all of these events that are scattered all over, and unfortunately, none of them are correlated with any particular source. So another complementary measurement was done with muon neutrinos, and these are the events that are required to travel through the atmosphere. And basically, what we see also an axis of astrophysical events. And the highest event that was observed was roughly a few PeV. But as I said, the muon neutrino are much worse energy resolution. So this is how this high energy event looks like. So this is basically a lower bound on the energy. So the true energy is probably higher, but we can't really tell what is it. So we observed the atmospherical flux in two channels. Now, what can we do with muon neutrinos? Their angular resolution is pretty good. So we can also look for a correlation with other experiments, like, for example, Fermi satellite, which detects photons. So unfortunately, so this is our event. And all these other dots are sources discovered by Fermi satellite, and nothing points to our neutrino event. So this is still puzzling. We would expect that given a large flux of cosmic neutrinos that we've discovered, which is roughly consistent with the flux observed by the Fermi satellite, that there should be some correlation, or we could find at least one event that overlaps with the Fermi catalog, but this is not the case, so this is still a puzzle. And then I don't have, this is like literally a couple of last slides, but this is timely. We know about the gravitational waves, which have created a lot of news, and this basically came from the binary neutron-star merger. So we, of course, looked for a correlation with this particular event. So this gravitational wave, if you look at the distance, is a function of energy for different basically different types of probes. So optical, X-rays, gamma rays, neutrinos, and cosmic rays. We don't expect to see gamma rays from a large portion of the sky. So this is opaque to photons, but transparent to neutrinos. The one event that happened, it was lucky to happen, like not so far. It's 40 megaparsec. But as you will see, we have not seen neutrinos coming from this source. So what we did, we searched for neutrinos in a given direction, so which was determined by the gamma ray follow-up or optical follow-ups within 500 seconds and 40-day time window. By basically, we were able to just place limit, and there's no coincident events found. So in the future, we just expect that the flux of cosmic ray neutrinos is still very low. So we want to upgrade, which is not easy. So the plan is to build like really a neutrino observatory in Antarctica. And so here you see the ice cube, this 1 cubic kilometer detector. And the plan is to drill strings even further apart. Now we know that we could see that the absorption length, at least in the bottom of the detector, is 400 meters instead of 200 meters. So we want to put these strings further apart just to keep the cost under control. And basically, there will be additional components. So the surface veto will be used to veto more efficiently cosmic ray muons. There is a plan to deploy radio array, which would be like a 100 kilometer square, where the antennas can be separated even further apart, like 1 kilometer, because the absorption length is even larger. So basically, we want to have an instrumented value of 10 kilometers, roughly the same budget as IceCube, and the construction would happen in 2024-32 if this project is funded. So this is one of the geometries that's proposed. Of course, it would be nice to have IceCube in the center of the detector, but there is no way to deploy anything that would run into the current infrastructure of the station, runway, etc. So this may not be the most desirable design, but that's what's being considered. And here you can see how much improvement you could get if you have this next generation IceCube, or if you just continue with IceCube as it is. So basically, you can, with a significant investment, you can really start to pinpoint astrophysical sources. So this is the plan line or construction. So there is ongoing R&D to develop. So we want to change optical modules. We want to make the drill more efficient to keep the cost lower. The design phase will be ongoing, and the construction is later in 2025. Now, how does it look compared to what's going on in Europe, which is relevant, I think, here? So KM3net is basically a competition for IceCube. The plan right now is to have 2 detectors, one in Italy, one in France. This would be dedicated to oscillation physics. This will be dedicated to astrophysical neutrino. And the first part would create a detector of roughly 1.2 kilometers square, but the goal is to go to 10 kilometers or even more funding permitted. So this I would like to conclude. The era of neutrino astronomy has just begun. So we've discovered astrophysical neutrinos. We have measurements with astrophysical neutrino flux. And now we're in the phase of model testing. But basically what we want to see is to observe the first source. And for this, we feel that we need a bigger detector. So I'd like to thank you. And I'd like to thank you with this slide, this was taken by one of IceCube shifters. There are 2 of them who stay in the winter to take care of the detector. So every week we get reports with this one, with these nice pictures of auroras. I unfortunately could not witness this, but maybe I'll travel at some point to the north, which it's easier to observe. So thank you.
Thank you so much. It was really a wonderful story. And then I guess we have many questions.
The way you showed it, it seems that those pods used for detecting light are in the ice, and therefore it's not possible to exchange them. How many of the pods have failed so far?
I didn't understand the question.
How many of optical modules have failed?
Have failed. So 98% is working.
And do you have any predictions how long will they work?
Indefinitely. So the problem is that with ice moving, at some point the strings will no longer be vertical, so they will start
Losing the connection, the wires would get cut.
Well,
I guess the cables are loose, so they allow movements.
They allow movements, but it will not be optimal. But right now, so the requirement when we proposed this detector was that they should be operating for 15 years, but that number was just taken. So basically, we don't, now that we've seen how well they work, we don't see like why we should not be able to take data in 10 years from now. So of course, the computers and everything that's on the surface is being upgraded. You can reprogram some parts on the dumb optical module part, but we think that within this 15 years we will really move to the larger detector.
And you don't plan to use the current array in the new detector?
We would like to.
Okay.
But as I said, so the expectation is there is no really a reason for anything to break. They've been pretty stable.
Because there is no way to get them out, right? That they're in the ice embedded and
no. So that was the biggest challenge, to test them to death, so that when you deploy, they will really work. And that was the biggest worry.
And the 2% that did not work, they did not work from the start, or did the failures accumulate?
From the start, so there was
okay,
yes.
So basically.
Yes,
so,
and
okay.
we're also working on improving the uptime. So there are some runs to take the calibration runs. So we're trying to minimize them. Initially, there were different. So there were periods of time between one run stops, the other one starts. So all of this is has been eliminated. So right now we have like 99% uptime. And basically the real goal for having this really high uptime is for supernova neutrinos. Even though we will not be able to see individual supernova neutrinos like Super K could, but the signal in our detector would be the raise-off rate of all optical modules, and we would not want to miss it.
Okay, thanks.
I have a question, namely, can you explain why you haven't seen anything in neutrinos from the merger of these two neutron stars? Was it too far away, or can you calculate how close should it be that you will see a signal in neutrinos?
So this calculation was done. Now whether the calculation, you can trust the calculation, there is no reason not to trust, but there are lots of assumptions that go into these calculations. If I can find it. Yeah, I basically went through this very fast because of the time. So here are the models. So there are different lines, like the red, blue, and purple, and they basically tell you like how prompt the emission can be. And these angles are these are parameters that you can set in the model. So how far off axis you should see the emission. So this basically spreads. This is the reasonable spread within a model. What you should expect. So now you can probably rule out one of them, and this is again for 500-second time window, plus or minus with respect to the gravitational wave. But I think the neutrinos are interacting so weakly that we basically don't have sensitivity. So with a bigger detector, or maybe with a bigger detector, this would be possible. And for this, with even larger time window, there is no way for us to detect. And Antares and IceCube, basically the difference is in the size. So IceCube has a much higher sensitivity, but basically these are just a couple of models that have been tested. They're considered to be optimistic. So all these gravitational waves were followed by a prompt gamma ray emission. And in this particular case, it is expected that we would not be able to see a neutrino.
Is this an answer? You satisfied? Mm-hmm. More questions? I may add a comment. I do remember those times when Amanda has not produced any signal. The important component, I would even say almost the founder were the Swedish groups, and that's how I know the details. It was a real disaster. At a certain moment, all financing agencies, including university authorities, refused to do anything with those experiments. No financing, no future planning, no allocation of technical means or support, nothing. Because they said nothing is seen, so they fail.
So there's a difference
it was really a tragic story on the level of Amanda, of this pilot setup. And then to somehow go through it and get financing and go to IceCube, I think it was Francis Halsen's great.
Yes. And how the US works.
Yeah,
I think
yes.
they accept failure, and you can see this in business. Like you're allowed to go bankrupt a couple of times before you get successful. And
they're very stubborn, the financing agencies. They simply said plainly no. I remember on the level of our faculty council in Uppsala, we also said, well, they don't produce anything, no papers, no conferences, nothing, no signal. They just eat money and equipment and people, so we just finish with them. No future. About the same like it was with gravitational waves, right? Same story, so one should be patient with science, definitely.
So to add to this story, I've read an interview with Francis Halsen, who said, well, you should trust your literature and use them when you make predictions. But given what was known about ice properties from geology at that time, if he knew about this, it would not be possible. But he was not aware of the studies from geology, so he just boldly proposed it, and it flied.
Yeah, well, there's...
Maybe I have a comment, a question. I think it's truly fantastic that in these times of prevailing anti-scientific attitude, there is somebody willing to pay for these fantastic experiments. And I have a question. Could you say us briefly how much all this was at the cost, and if the decision to pay for that was only scientific, or there was some political element, like with superconducting supercollider? At some price tag, of course, the politics enters the decision. Can you comment on that?
Yes, so LIGO and IceCube are the flagship of the NSF. They really believed in this. So, of course, the cost is different. So LIGO is billions dollars. IceCube was, in the end, 240 with some contribution from Europe. 240 million, yes. And the operational costs are going, so right now it's just operational cost, which is not that high, but the challenge will be to upgrade. So the plan for upgrade, which I didn't mention, is that the funding agency wants to, for us to prove that our improvement with optical modules, so optical modules were optimized for muon channel, actually was the golden channel. So that means that our PMTs were facing down just because we wanted to see neutrinos that are traveling through the Earth. Now we see that the most exciting events are those electron tau events, and in order to increase or improve the angular resolution and the efficiencies, you actually want to have a coverage in all directions. So this is one change that we want to introduce. And then again, you need to show that the technology works. So IceCube has recently submitted a proposal to NSF for a smaller amount of money, like below $10 million, which is a mid-scale proposal. And most of it is to develop the drill to lower the overall cost. But so the feedback that we got is that that's all fine. It's an important step towards the bigger detector, but scientifically it needs to stand on its own. So it needs to. So this includes like very limited number of strings instrumented with this new optical modules, and then we would want to deploy them like very close to each other and do the oscillation physics, because that's what you can do with the focus on tau neutrino oscillation. So that's the plan. It has not yet been funded, but they don't do it as well. This is the necessarily first step, so it needs to be scientifically driven, and it needs to make sense for the next step. So, but money is tight and everybody is getting cut, so we'll see. I'm optimistic.
More comments? Ja sobie pozwolę jeszcze coś dodać po polsku, bo już to będzie nie bardzo związane ze stroną naukową. Otóż mniej więcej 1,5 roku temu u nas w kinach w Warszawie szedł film Antarktyka. Ja go zobaczyłam przez przypadek w kinie Kultura, poszłam i stanowiłam 100% widowni. Następnego dnia powiadomiłam u kogoś, bliską mi osobę, która poszła i stanowiła znów 100% widowni, a pan operator się już wściekł i powiedział, dlaczego pani musi tu siedzieć, może moglibyśmy razem pójść do domu, no ale pokazał film. Otóż ten film to był pełnometrażowy, aczkolwiek amatorski film kogoś, kto spędził noc na biegunie. noc, to znaczy właściwie cały rok dziewczyna tam była. I nie wiem, bo ty zdaje się też widziałaś to, ale dla mnie to było coś po prostu niepojętego. Znakomitego, najwyższej klasy. To jakoś tak przeszło niezauważone zupełnie. Więc trzeba czasem mieć oko otwarte i patrzeć.
Tak, ale że spędzić tam cały rok na biegunie to jest naprawdę bardzo, bardzo
Ta
trudne.
dziewczyna zresztą, bo to dziewczyna była autorką, ona zresztą tam zawarła związek małżeński, a rodzina była obecna przez Skype'a i było wszystko filmowane. No dobrze, to podziękujmy może Joannie bardzo
Dziękuję.
za przyjechanie, odwiedzenie ojczyzny i za referat. A wszystkim życzę wesołych świąt i następne spotkanie jest w połowie stycznia.